In this video, we're going to explore determining the species of an unknown from a possible list using the KSP values and some reaction data. So in this case, we've got a beaker. It's going to have half a liter of water in it, and one of these salts, we don't know which, is going to be put into it. This is going to be given time to form an equilibrium. We will saturate the solution with as much of the material as it will allow to dissolve. At that point, we're going to filter off the solids. The dissolved material will stay dissolved. The maximum amount of whatever ions we're allowed to dissolve will still be present. What we're then going to do is we're going to add 200 grams of sodium chloride. Well, this is going to flood this solution with an enormous amount of chloride. Generally, when we think of concentrations of ions with these incredibly small KSPs, we're getting a fraction of a mole. But 200 grams of sodium chloride in half a liter, that's going to be multiple molar. There's going to be a lot of chloride around. The common ion effect is going to make either silver chloride or lead chloride precipitate out. Given the vast quantities of chloride, we can assume nearly all of the cation will precipitate as well. Well, as that occurred, 2.32 grams of a precipitate formed. Using this info, can you determine what the original salt was? First, go ahead and pause and just conceptually plan how would you get this info? What would you need to know to backtrack to go back to the original? Coming back, we'll walk through how to approach it, and then we'll pause once more for calculations. All right, if you're back, how to approach this one. Just conceptually, I want to know what that original salt was, but I really have no information about the original salt. All the information I do have comes from once we crash it out of solution. So what I really have is I have 2.32 grams of salt. But it's a final salt. This is either silver chloride or lead chloride. Well, I could use that to find moles of both species. So I could know how much silver I would have had or how much lead I would have had. We don't know which one it is, but it was going to be one of these two cations. And so using this weight of the likely products, when you flood the system with chloride to crash all the cation out, we could figure out how much of each of these I would have had should it have been a silver or lead salt. Well, however much we find, that's the equilibrium amount. The whole original idea was the salts reached equilibrium, so whatever amount of silver or lead I could obtain must have been the equilibrium amount allowed in my half liter. So if I can find the moles of lead in that half liter, I can turn that into the molarity of those ions originally. What must the molarity have been at equilibrium? Knowing that, well, I have some KSP values. I can figure out what the molarity at equilibrium for each of these should be, and I can compare back to what I found it must have been to give me 2.32 grams of whichever of these we formed. And so using the weight of the solid at the end, we can follow two paths, a silver path and a lead path, to figure out how much of each of these we have, what the molarity of it would have been just before you'd added sodium chloride, and therefore, which of these salts would have given you that molarity. Go ahead and see if you can calculate that and come on back. All right, if you're back, well, let's give that a shot. I've got 2.32 grams of unknown. So we're going to do two of these. We're going to do one of these where it's silver, and we're going to do one of these where it's lead. For a silver route, well, it's going to be 143.3 grams in 1 mole for a silver chloride. So that would give us 0.01619 mole of the silver. And for the lead to chloride, well, this is 278.1 grams in 1 mole, which is going to give us 0.00834 mole of our lead chloride. And sorry, up above, that was our silver chloride. However, they are 1-to-1 with the ion. So 1 silver chloride would give us 1 silver ion originally. So 0.01619 mole of silver ions must have been in solution to be crushed out when we flooded it with the sodium chloride. Same with our lead down here. For every 1 lead chloride, we're going to have 1 lead ion. So 0.00834 mole of lead ions. Assuming that the sodium chloride being in such excess would push almost the entirety of the cation out of solution, within air, this must have been how many moles of each of these would be in solution. Well, we need to compare this to molarities then, because these were really in half liters. So each of these are in 0.5 liters, 0.5 liters. And what we'll find then is that for the silver, if it had been silver, we would have had 0.0324 molar silver ions. And if it had been the lead, we would have had 0.01668 molar of the lead ions. So to get our 2.32 grams of whichever species this is, when we added it to a half liter, we would have had this molarity of those ions to begin with. We'll go back to our species here. We can go ahead and zoom in a little. Here were our two options, our silver and our lead. Here were our original species. We can use the KSP to figure out what the concentration of each of these ions should be. For our silver bromide, our KSP is going to equal the silver times the bromide. For our silver chloride, it's going to equal the silver times the chloride. For our lead 2 bromide, it's going to be the lead and bromide squared. And for lead chloride, it's going to be the lead and the chloride squared. So there's a little bit of difference in these calculations. So as our solid breaks apart, we're going to make X and X amount for our silvers. We're going to make X and X amount for silver chloride as well. We're going to get X and 2X for lead bromide, and we're going to get X and 2X for lead chloride. Remember, every time a lead chloride breaks apart, it makes 1 lead, but it makes 2 chlorides. Well, this means our KSP is going to just equal X squared for our 2 silver salts, but it's going to equal 4x to the third for our lead salts. So 2x squared is 4x squared, and then times x for 4x to the third. So we can plug in each of our KSPs and either square root each side or divide by 4 and cube root each side, and we can calculate out what the x value for each of these should be. So what is x for each of these salts? How concentrated should our silver or our lead be? Well, if we run that for silver bromide, we'll get 7.35 times 10 to the minus 7. If we do it for silver chloride, 1.3 times 10 to the minus 5. For our lead bromide, we will get 0.01669, and for our lead chloride, we will get 0.0162. If you think about our values for a minute, our silver chloride has a larger KSP than our silver bromide. 10 to the minus 10 is bigger than 10 to the minus 13. And so we should have more of it dissolve, and that's what we actually see. The concentrations we get are about 2 orders of magnitude larger for the chloride salt there. Lead bromide and lead chloride are pretty dang close. We find that our concentrations we calculate out are also pretty dang close. When we go and compare it to our options, we needed our silver at 0.03, and neither of these are anywhere near 0.03. If we look at our lead, if that had been our original salt, 0.01668, well, the two of them are pretty close, but 0.01669 is closer than 0.162. So within a little bit of air, it seems to pretty closely match this X value, which came from our lead bromide. So based on the amount of salt that we created when we flooded the saturated solution with chloride, we were able to find the likely concentrations of whether it was silver or lead that had been in the original salt. And of the 4 options, only one of those really lines up with that value. The second lead is close, but this lead is much more on the ball with what our calculation from the collected solid showed. And so in all likelihood, the original salt was the lead bromide.